Alright, so in the last video we started, doing some basic combinatorics, so counting, that's the math of counting, I guess. And so we introduced, the factorial and how to count with less and the multiplication principle and pigeonhole principle and all that stuff. And we did all that while learning some basic theory. So in this video I just want to, expand on that and look at some more particular applications of it. And particularly we're going to be looking at the binomial coefficient, which is interesting in its own rights, and we're probably going to have an extra video on it. So first, before I do that, I do want to look at a particular application of the multiplication principle, and that's branching off from the factorial, and it's going to be for arranging a list of size k. So let me explain exactly what I mean. So first of all, recall that there are exactly n factorial, so n exclamation mark, ways of arranging an n distinct element list. And so n factorial is equivalent to n times n minus 1 times n minus 2 all the way down to 2 times 1. So it's the products of all the first n natural numbers, excluding 0. So now I want you to consider a list of size k, but with n available objects as elements. So before we had a list of size n, and we had, n available distinct elements. Now it's kind of like we want to take a list of size n, with n distinct elements, but instead we want to take a sublist of that, a list of size k instead. So, and that one, instead of k choices for first element and then k minus 1 choices for a second one, and so on, we'll instead, start with n and then n minus 1 and then minus 2 and all that. So for example, a list of size 3 that contains the symbol a, b, c, d, e without repetition. So such a list could be ABC, but another list could be ADE or CDE, and they don't all necessarily share all their elements, unlike with the factorial application. So as I said, for the first element in the list, there's going to be n choices of objects, and for the second, there's going to be n minus 1. So in our case, the one with A, B, C, D, E, for the first object, I can either pick A, B, C, D, or E. Then for the second, I can, depending on what I picked on the first one, say I picked C, for example, then I only have A, B, D, or E as a choice, so I've got n minus 1 choices. And then I can keep going to n minus 2, then n minus 3, kind of like when we did with a factorial. However, since there's only k slots in the list, the last element is going to be n minus k plus 1 available choices, instead of 1 available choice like we'd have normally. So in our case, we've got a list of size 3. So say, for example, for the first one I choose A, for the second one I choose B, and for the last one I've only got 3 choices. And if I check the n minus k plus 1, I've got 5, minus k is 3, that's going to be 2, and then I add 1, and that's going to be 3, so I've got 3 available choices. And so applying the multiplication principle, n choices for the first one, n minus 1 choices for the second one, all the way to n minus k plus 1 choices for the kth one. And so, that's going to give us n times n minus 1 times n minus 2, all the way to n minus k plus 1 choices in total, thanks to the multiplication principle. So that, once again, it's a really powerful application. Well, it's a really powerful tool to help us count different types of things. In this case, it's going to help us for this. And there's actually a convenient way to write this in terms of a factorial, because this is analogous to a factorial in some sense, except that it ends earlier. So it would be nice to be able to write it more concisely in terms of factorials. So if you note that n times n minus 1 times n minus 2 times ... times n minus k plus 1, that's the same as taking n times n minus 1 times n minus 2 ... times 2 times 1, all divided by n minus k times n minus k minus 1 ... times 2 times 1. So basically, this part of the division on the denominator, it appears after the n minus k plus 1. After n minus k plus 1, if I kept going, I'd then have n minus k, then I'd have n minus k minus 1, and so on. So if I take a whole factorial here and divide it just by that, then it's like removing that part of the factorial, so you only be left with the part that we care about. And so that's why we write it afterwards, as n factorial, that's the top part, times n minus k factorial. You can see here that this is n minus k factorial. And so that gives us a nice way to talk about the taking k sublists of an n element list. So it's like arranging the whole list with n factorial elements, and then I remove this n minus k factorial in the bottom. And you can reinterpret that as arranging an n-sized list and removing all the n minus k arrangements. I wrote n minus k elements, but it's removing all the arrangements of size n minus k from it. If I pick a sublist of size k, you can actually kind of think about that as being analogous to taking a sublist of size n minus k. and removing all of your arrangements from that to only be left with possible arrangements that you'd have in a k-element list. It's kind of like splitting your list into looking at the ones you don't care about. So you take all the possible arrangements of that, and then you remove it from the total amount of possibilities you have. So, we've counted lists, and lists are nice. But sometimes we'll also be wanting to count subsets, and that's where our next line of investigation comes. So, what about counting sets, which restricts us on repetition, but they give us liberty on order? So what I mean by that is, in lists, I'm restricted, the list A, B, and C is, specific to this order. This is not equal to the list C, B, and A. Because, that's just what lists are. But, the subset, I'm not going to write it, but the subset A, B, C is equal to the subset C, B, A because order doesn't matter. However, we've got a restriction on repetition. I mean, we've been counting distinct element lists, so it doesn't really apply to the situations we had before. But I could have the list AA. That is a valid list. But the set AA, that's not valid. I can't have repetition in a set. So a set would have just A as an element, and I guess you could accept the sets of that have AA, but you'd have to specify that this is actually the same set as A. So that's where it becomes a little more annoying if you want to talk about sizes of sets. So it's better to just not accept these types of sets. So yeah, and now we want to count sets and sets, so that's going to be a little different than lists. And it turns out that the number representing the number of k-sized subsets of an n-sized sets has some very nice properties. And this is analogous, k-sized subsets from n-sized sets. This is analogous to what we just looked at with k-sized sublists of lists. But instead we're doing subsets, so the computation is going to be a little different. But the one for subsets actually has some really nice number theoretic properties that we're going to look at. So I want to define if n and k are natural numbers, then this parentheses with n at the top and k at the bottom, I'm gonna pronounce this as n choose k. This denotes the size of the set P of big N small k, which is going to be all sets k such that k is a subset of big N, and that the size of k is small k, and we also want that the size of big N is n. So basically, what is this saying is I can take any set of size small n, right, and then I take all its subsets that are of size small k, and to make this new set here. And so this is a subset of the power set of n, which is why I'm using the p here. We haven't looked at the power set, but p of n for some big set n is just going to be all the subsets of the big set n. And this is going to have size 2 to the n. I'm not going to say why, but you can try and figure this out yourself from the multiplication principle, why something of pn would have size 2 to the n. So let me just remove that. So this is going to be a subset of that. And so it's denoting the size of that set. And note that, I'm saying small n, small k, and here I'm using this big N here, so it really doesn't matter what the set is. All that matters is that the size of the set is of small n. So this is applying to all sets of size small n, and all of our subsets of size k. And it doesn't matter what the set is. So this is really about the size of a set and not about particular sets. So it's the number of k-sized subsets from a set with n elements. Yeah. So clearly, n choose 0 is going to be equal to 1. Now, this is because the empty sets, so the set, like this denotes the empty set, so the set with nothing in it. I can also write this as curly braces with nothing in them. This is considered a subset of every set. I mean, every set has the trivial subsets of the empty set and the set itself. So every set, has at least 2 subsets. And so yeah, as I said, so that allows us to see that n choose 0 is going to be 1, because I pick all the k-size subsets, well, all the 0-size subsets of a set, and only 0-size set of all sets is going to be the empty set. And so that is a subset, so there is one way to pick that. And so that means there's only going to be one element to this p and k. And n choose n is I'm taking all the n-size subsets, and the only n-size subset of an n-size set is the set itself. So p and k is only going to have one element, and it's going to be the set itself. So that's why that n choose 0 is equal to n choose n is equal to 1. And you could also note further that n choose k is equal to 0 if and only if k is bigger than n, because I've said any set has at least two subsets. So the size of this normally would at least be 2 if this k number is smaller than n, because then I can pick any type of subset that fits that. But any subset always has to have a smaller size than the original set, or the exact same size. So if k is bigger than n, then this definition just doesn't apply really. So I can note that this is going to be equal to 0 for that case. So, and I could also, I guess, further extend the definition, because here I said n k belong to natural numbers. I guess if you wanted to, you could say if k is smaller than 0, so instead we let k be an integer, then this is also equal to 0. So, before we actually look at some explicit formula for n choose k, I'd first like to look at properties. This might not be something you're used to doing when looking at certain objects. Maybe first you'd look at exactly what the object is in terms of explicit formulas, and even if it looks complicated, and then look at properties. Well, instead, we're going to look at properties first, and then we'll get the explicit formula from that. So one important property of it is this proposition here, and it's called a recurrence relation because it defines n choose k in terms of smaller n choose k's in some sense. And this is kind of analogous to the principle of induction, where I say that if this element is part of a set, it implies that this element plus 1 is also part of a set. And recurrence relation are in some sense related to that. And it's the idea of defining an object by some initial condition and then saying some property that defines the sort of next object, so that it defines all the objects. So anyways, the proposition is that n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k for any k that's smaller than n. And I say smaller than n, it also needs to be bigger than 0, because otherwise this k minus 1 here is going to be negative. And I did say we could have defined it as it being 0, but it's better to just not. And so well, I guess you could, and then it works as well, but it doesn't really matter. So let's look at a proof for that. It's relatively intuitive. So let's take each element of p and k, and remember, this is the size of the set we're interested in. And we can remember each element of p and k is going to be a set itself. And so each of those sets, they can fit in one of two classes. When I mean classes, they're one of two types. So if I take any element n0 that belongs to big N, an element big K which belongs to p and k, so this is going to be a subset of big N, it either contains n0 or it doesn't contain n0. That makes sense. For any given element of a set, any subset of that set either contains the element or it doesn't. So that's just one way I can classify them in. So let's S and 0 contain all the elements of p and k, so all the sets inside p and k, because these are sets, that contain n0, right? And then p and k, so this backward slash means I just remove Sn0 from p and k, because remember Sn0 contains all elements of p and k, so it's going to be a subset of p and k. And so this one's going to contain all the elements of p and k that do not contain n0. So I'm just splitting all the elements of p and k into two sets, the ones that contain n0 and the ones that don't contain n0. Okay, so let's first look at the size of Sn0, right? And I claim that it's equal to n minus 1 choose k minus 1. And so the reason why I can do that is that I can remove the element n0 from each set inside Sn0, right? Without actually affecting the size of Sn0. And if you think about back to last video, it's specifically you can construct the bijection fs equals s remove n0. I've written n0 like this. It should have a set around it because these are operations in the sets. So let me just clarify that. And I'm not going to prove that this is a bijection, but it is. And so anyways, you can do that without actually affecting the size of Sn0. And so that means that Sn0 is going to have the same size as the set, which has all those elements where you remove n0. And if you think about it, then at that point, all the elements of Sn0 are subsets of of big N, right? Except they each don't contain n0, so you can think about it as subsets of big N remove n0, right? Because each of them don't contain n0 anyways. So you can kind of just forget about n0. And each of them, since we've removed n0, they're going to be of size k minus 1, since originally with n0 they were size k. So it's like choosing all the subsets of size k minus 1 from an n minus 1 set. And so, that's the definition of n minus 1 choose k minus 1. So that gives us the size of Sn0 by that bijection as well. And so that gives us the size of one of them. And let's look at the size of the other set, right, which is pnk remove Sn0. And I claim for a similar reason that this is going to be n minus 1 choose k. And why is that? Well, none of those contain n0, so once again I can think about looking at the original set n remove n0, which is going to be a set of size n minus 1. Except all these guys are going to be of size k, so it's going to be the same case as before, except now all the guys are size k, so instead we're going to have n minus 1 choose k instead of n minus 1 choose k minus 1. And so the final piece of the proof is just to note that, Sn0 and Pnk remove Sn0, we're going to partition Pnk. So that means that the size of Pnk is just the size of Sn0 plus the size of Pnk remove Sn0. And so, I've looked at the size of each of them independently. So I'm going to have n minus 1 over choose k minus 1 plus n minus 1 choose k. And so that gives me, the total size of my sets as we need here. So that completes the proof. So once again, we're still want to keep away from the explicit formula, but there's something that we've got now. We've got this recurrence relation, and we've got, well, I'm not going to go all the way back, but we've got the initial conditions on n choose k. And so, using only those conditions, n0 is, well, n choose 0 equals 1, n choose n equals 1, n choose k equals 0 for k is bigger than n, and n choose k equals n minus 1 choose k minus 1 plus n minus 1 choose k for k is smaller than n. I can visually start building up n choose k. I note that I can start from n equals 0, so the empty set, and start building up, because it's just going to, n can only take natural numbers. And so I can build this whole grid here, I build it up in one go. But so basically, the way to think about this is that this column here represents n, and this row represents k. And so each element in the grid here represents some value of n choose k. So let's look at, when n is equal to 0. Well, it makes sense that when n is equal to 0, 0 choose 0 is just going to be 1. Because, anyways, I've got the n choose 0 equals 1 for all of them. So, I've got the 1 here. And in fact, all of these other ones here that you see, in this diagonal and in this vertical, is all the cases where k is equal to 0, or when k is equal to n. So, here I've got k is equal to 0, down here. So those are all the cases where k equal to 0. Let me just highlight them. And all the cases, actually I'm going to use a highlighter, it'll be easier to see. So let's just color these guys in, like that. And then I've got all the ones where k is equal to n. 2 equals 2, 3 equals 3, 4 equals 4. And so this is just from the initial conditions that I've constructed these guys. And all the zeros you've got above on the top, you don't really have to be concerned about them. I could have just not them in. This is also, from the condition that n choose k equals 0 for k bigger than n. So let's look at the next one here. Let's look at this 2, right? So this is going to be, if I look down, this is going to be 2 choose 1. And I want to show that 2 choose 1 equals 2. Well, I take 2 choose 1, and I'm going to use this, this identity here. And I guess I can highlight that as well. Like this. There. So I'm going to use this identity that we just proved. And so, I know it's that k is smaller than n because 1 is smaller than 2. So I've got that 2 choose 1 is going to be equal to 1 choose 0 plus 1 choose 1. So what's 1 choose 0? Well, 1 choose 0, we've already looked at it. And it's going to be this one here. 1 choose 0. And it's going to be 1. Okay? And 1 choose 1 is going to be 1 choose 1. So it's going to be 1 as well. So I know that 2 choose 1 is going to be 1 plus 1, which is equal to 2. So okay, that works. And visually on this grid, I'm just looking up and to the right, and I'm just adding these two entries like that. Going up corresponds to changing this top index to n minus 1. Staying on the same column corresponds to taking this guy here, n minus 1 choose k. And going to the left corresponds to taking n minus 1 choose k minus 1. And so I can keep doing this. For the next one, this 3 here, I go up and to the left. And so I take 1 plus 2 is going to be 3. Same here, I go up and to the left, is going to be 2 plus 1 is going to be 3. And then for the next row, I take 4 is going to be 1 plus 3. 6 is going to be 3 plus 3, that works. 4 is going to be 3 plus 1. And next row, 5 is 4 plus 1. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And I can keep going like this. I've got 1 plus 5 is 6. 1 plus 6 is 7. Go down here. 1 plus 7 is 8. 1 plus 8 is 9. So something you might already notice here is I've just got 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is going to keep going And similarly on this sort of diagonal here, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Because you might have noticed already that there's a symmetry, across these numbers. You've got 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. There's sort of like a vertical symmetry like that. Here, same here, 1, 6, 15, 20, 15, 6, 1. It obviously reflects. It's kind of like a palindrome if you think about it. And, I can keep going. I've got these guys here. If you're familiar with the triangular numbers, you might have noticed that these guys are the triangular numbers. And, if you're even more familiar, you might have noticed that these guys are the pyramidal numbers. And so, you can keep going, and so on. You've also got a nice property here, on this 7th row. You've got some multiples of 7 only. And these are all interesting properties of this structure here that I'm going to qualify in the next slide, and we're going to mainly look at those properties in the next video. But it's quite an interesting thing to look at. And so anyways, yeah, you can see how we can visually generate all these numbers just by starting from those initial condition and using this recurrence relation. So that's why recurrence relations are pretty powerful. And of course, this isn't going to help us for computations of really, really big numbers, because you don't want to draw this entire grid. And that's where we're going to have to find an explicit formula afterwards. But it's definitely worth looking at in this format. And so, one way to redraw this, because, this is kind of like messy. I've got one vertical here and one diagonal there. Even though I've noted this symmetry, it's kind of weird to have a sort of like half diagonal kind of symmetry. How's the thing? And you see that this forms a sort of triangle. So instead, we're going to redraw this as a sort of isosceles triangle called Pascal's triangle. And so here there's even more entries to this thing. But it's even easier to see, that every element is just the addition of the elements on top of it. I've got 1 is 1 plus 0 something on the side, or I've got all those ones on the side from the initial conditions, I guess. And then 2 is 1 plus 1, 3 is 1 plus 2, and so on, And so, from this we know that 14 choose 6 is 3003. So I can look, I say this is column 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I'm at this column there. Oh, let me change back to a pen. I'm at this column here. This row here, sorry. And then column is going to be 0, 1, 2, 3, 4, 5, 6. So I'm up here. If this is 14, choose 6, 3003. So I can use Pascal's triangle to kind of, look into that. So once again, next video we'll see more properties of this triangle. So why did I write binomial coefficients here? Let's see. Why is this not moving? Hello? Oh god. Glitched. So, sorry. N choose k is also known as the binomial coefficient. And, maybe you'll see why it's called like that here. So if I write x plus y to the 0, right, that's going to be equal to 1. Because, anything to the 0 is equal to 1, so that's pretty easy. If I take x plus y to the 1, well, I can FOIL. Well, I don't even need to FOIL, because, if this is to the 1, this is just the same thing. So it's going to be 1 times x plus 1 times y. And note I've written out the coefficients explicitly here instead of writing x plus y. If I take x plus y squared, now I can FOIL to take, x times x is going to be x squared, so I've got 1 times x squared. Y times y is going to be y squared, which is 1 times y squared. But unfortunately, this isn't the freshman's dream, and I can still take x times y to get x times y, and then y times x to get y times x, and so I've got x times y plus x times y gives me 2 times x times y, which is what I've got here. This is just the basic FOILing technique, and this is the expansion for a squared binomial. And yeah, if you're not really familiar with what a binomial is, this here is a binomial. It's 2 terms, and then I'm expanding it with these powers here. Bi for 2. Yeah, it's a polynomial has multiple terms. This is a binomial because it has 2 terms. So anyways, then if I look at x plus y cubed, once again I can FOIL out, and I'm not going to do the whole FOILing here, but you can try to do the FOILing on your own. To get 1 times x cubed plus 3 times x squared times y plus 3 times x times y squared plus 1 times y cubed. And I can keep going, with to the 4, and I can do this FOILing out, which is 1 times x to the 4, 4 times x cubed times y, 6 times x squared times y squared, 4 times x times y cubed, and 1 times y to the 4. And so if you don't already see it, I've kind of spoiled it by moving forward. But if you don't already see the connection to Pascal's triangle, it might be easier for me to first, remove all these x and y terms. And once I do, and I only keep the coefficients, now you should notice I've got 1, I've got 1, 1, I've got 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And these are exactly, the elements of Pascal's triangle. And you'd see that if you expand x plus y to the 5, maybe that's an exercise for you to do, you'd have 1, 5, 10, 10, 5, 1, and which is the next, row in Pascal's triangle. And you can keep going like that for infinity. And, if you're not convinced of this Pascal's triangle, you can just check that each element, is the addition of the rows before. I'm not going to switch back to the old picture of Pascal's triangle. And so, that's why this is called the binomial coefficient, because keep in mind, all these numbers in Pascal's triangles are n choose k numbers. And, it's just a visual way to represent the numbers n choose k. And so each of these numbers here are coefficients of a binomial expansions here. On the second row, it's going to be the coefficients, well, third row, I guess, the coefficients of the expansion by a power of 2. And then on this fourth row here, or fifth row, I guess, it's going to be the expansion by the coefficients of expansion by a power of 4. And I've written it out here, but we should probably, prove it. And so that's what we're going to do. Let's prove it. And this theorem is specifically called the binomial theorem. Okay, so for n is natural, right? And x, y are real numbers. I've got x plus y to the n is going to be equal to, so remember this is a sum notation. So this is the sum from k equals 0 to n. So basically I'm taking this expression here, and k is called the index, and I'm letting k range from the 0 all the way up to n for the natural numbers. And I'm adding all these terms. So this is going to be, if I were to expand this would be n choose 0 times x times n minus 0 times y to the 0, plus n choose 1 times x times n minus 1 times y to the 1, and I keep going all the way to n choose n times x to the n minus n times y to the n. So maybe, if I look back at the last slide, and I put these coefficients back, you'll notice that when I expand these things, there's also a sort of pattern of the powers. The x power comes here from a cube, and then like the cube here, and it goes down in powers while the y goes up in powers. So they've got this anti-symmetry between the powers of x and the powers of y. Yeah, so that's why I've got this anti-symmetry here between the terms, which is x to the n minus k. So this is going to be, as x increases, this is going to decrease. And for y to the k, as the k increases, this is going to increase, in powers. So, this is what we're trying to prove here, because that's what I conjectured in the last slide. So let's look at a proof for that. And so we're going to use a technique from recurrence relations in general, which is called generating functions. And so specifically, this here is a generating function, where we take, it's a function of x and y. And, don't try and think about, when I say function, don't try and think about the functions in terms of sets like we looked at in the last video. I mean, it can be thought of as that way, but you'll probably just confuse yourself trying to, think about, what sets am I considering, and what exactly is it a bijection, is it an injection? Don't think about that. Just think about it as just being a shorthand for this expression for now. So anyways, this is going to be a sum from n choose k times x n minus k to the y choose k, and y to the k, sorry, from k equals 0 to n. So it's exactly the same expression I've got here. And I'm gonna start from this expression, I'm gonna manipulate it, I'm gonna show that it's the same as this expression. Okay? So let's see. So I'm just rewriting the identity here. And so let's see what we can get from that. So first of all, what I'm gonna do is I'm gonna take away this k equals 0 part of the sum, and this k equals n part of the sum. I'm gonna take them away from this summation. Okay? So I'm going to take them out of the summation. This is exactly the same as the summation as a whole. I'm just taking them out of the expansion. So I've got n choose 0 times x to the n times y to the 0 here, and I've got n choose n times x to the 0 times y to the n here. So I can simplify that. Well, I'm also doing a split, but you'll notice that n choose 0 is 1, n choose n is 1, y to the 0 is 1, x to the 0 is 1. So I'm only going to get x to the n and y to the n for these terms here. Now the second simplification I'm doing on this equality here is that I'm invoking the recurrence relation of n choose k equals n minus 1 to the k times n minus 1 to the k minus 1. So that, this guy here can split as an addition of n minus 1 to the k and n minus 1 to the k minus 1. And, I can expand that addition to get two separate sums. You could, if you're not convinced about that, just notice that multiplication distributes over addition, so I can split things linearly like that. And you might want to look at a few examples if you're still not convinced. I'm not going to try to convince you here. So anyways, this is a simplification we can do. Well, simplification. It definitely doesn't look like a simplification from what we have originally, but let's see what we can do with it. So the next thing I want to do is I want, from this guy here, I'm going to want to factor a term of x out of it. Because keep in mind, k starts at 1, right? So I can factor an element of x because I couldn't do it here. I couldn't take x out because then I get n minus k minus 1, but when k is equal to 0, that's going to be n minus, sorry, not when k equals to 0, when k equals to n, this is going to be n minus k minus 1, so x to the minus 1. And we don't really want to be considering fractions here because, we've got integer, and we've seen that the binomial coefficients are integers, so it's not really going to help us. In this case, though, since k starts at 1, I can factor it out to get, elements which work here. And same for here. Well, in this case, sorry, in this case, it's because k only goes up to n minus 1. And in this case, I can factor the y out because k starts at 1. And so that's also why I split it, so that I could have one term with an x at the front and one term with a y at the front. Keep in mind, x and y don't depend on k, so that's why I can also take them out of the sum. So let's just keep this result, and we'll move on to the next slide because we don't have much space here anymore. And so inscribe it at the top of the slide here. Okay. So this is exactly the same result that we had at the end. And so, I could write here at the front that gn equals that. Well, gn of xy. I'm not going to rewrite it, but whatever. Anyways, so from there, we can go even further. And we can look at this first term here, x to the n, and rewrite it a little differently as x times n minus 1 choose 0 is just 1, right? So I can, freely put this in. Times x to the n minus 1 times y to the 0. So x to the n minus 1 times x is just going to be x to the n, y to the 0 is going to be 1. So this whole thing is equal to x to the n, right? Now the reason I'm putting it into this form is that this form is analogous to the form of this summation here. It's for k equals 0, it's going to be x times n minus 0 minus 1, so n minus k minus 1, times y to the k, and then I've got this x here at the front that multiplies across the whole thing. So what that means is I can reincorporate it into this sum to get x times k starts from 0 this time because I've reincorporated for k equals 0. So I'm starting from k equals 0 all the way to n minus 1. And so now I've got this whole thing here. And now I'm going to do the same thing for the second term. Well, actually first, I can simplify this. Note that this here, this is exactly of a form of a generating function, but up to n minus 1. I've got n minus 1 here. This I could write as n minus 1 minus k instead of n minus k minus 1. And this goes up to n minus 1. So it's exactly of a form of, gnxy is equal to, we've seen that the sum, up to n of k equals 0. So it's important that k starts at 0. And choose k. X to the n minus k. And y choose k, right? I mean y to the k, sorry. So anyways, from here, if I just change this n to n minus 1, it's going to be exactly the same form that I have there. So anyways, now we want to do the same thing for this other guy. And notice, we've got to keep that x in front because it was factored out. So for this other one, what we're going to note is that this, I can first reindex things, right? Because here I've got a k equals 1. There I've got k minus 1. Here I've got k minus 1. So all the appearances of k inside the sum come with a minus 1 right after it, right? So I can reindex things so that k actually starts from 0, because when k equals 1, all these terms are actually going to be 0. So it may be easier to actually start with an index of k equals 0. But note that when k is going to be equal to n minus 1, it's going to end at this being n minus 2 and this being n minus 2. So we reindex things so that it starts at 0 and it ends at n minus 2. And we've got an equivalent thing here. And, this appearance of k here is a little bit of an exception. It comes on its own. So we have to rewrite it as k plus 1. And so, the reason I'm doing this is because this generating function starts from an index of 0. So we're going to need this index of 0. And so then, just like before, we note that this guy here is of a special form. It's n minus 1 choose n minus 1, because that's just going to be 1, times x to the n minus 1 minus 1. I could rewrite this as n minus 1 minus n minus 1, and so that's just going to be 0. So this whole thing is going to be 1. And this is going to be y to the n minus 1 times y to the front is just y to the n. And so this is of the same form that we have here, right? When k is equal to n minus 1, this here is n minus 1, same thing as there. This is going to be n minus 1, just like here. And here is going to be n minus 1 as well. So it's just the same form, and so I can incorporate it into the sum for when k equals n minus 1, so that I can add an index at the front, at the top. So I get y times k all the way up to n minus 1 at the top, right? And so then I can do the same thing. Note, that this is exactly the form of a generating function. So this is going to be y times the generating function for yx, because note that, I wrote for yx, but actually, I don't even need to consider it for yx. I'm not too sure why I wrote that symmetry here. It doesn't really matter. So anyways, I was going to say that then you can just flip things around in the xy, because you can, yx is the same as xy instead of a generating function. But in the end, this is still the same, so it doesn't really matter. And so anyways, we've got x times the generating function from n minus 1 of xy, and then y times the generating function of n minus 1 to xy. So I can factor this generating function at n minus 1 of xy to get x plus y times the generating function at n minus 1 of xy. So, and keep in mind, this is all starting from saying that g of n xy is equal to that. So if I move on, so we've got g of n xy equals gn minus 1 xy times x plus y. And so, we start g0 of xy equals 1 pretty clearly. You can do the sum yourself. You've got n choose 0. Well, you've got 0 choose 0, which is just 1. And then you're going to have x to the 0 times y to the 0, which is going to be 1 as a whole. And so when you sum it, you're just summing one thing. And so g1 is going to be x plus y times 1. So I've got g1 xy equals x plus y. And so, from here, I could keep going. I'd have x plus y times x plus y for g2, and then x plus y times x plus y times x plus y for g3. And I could do this by induction, I guess. And so from here, it's quite clear that gn xy equals x plus y to the n. And so that completes the proof. So it's a lot of manipulation for what seems like not much, but it's a really important theorem, which can be extended to binomial coefficients that don't necessarily have integers in them, to get sort of infinite series expansions for certain binomials. For example, when I have x plus y square rooted, I can expand this as a sort of infinite series of certain factors being multiplied by positive powers of x and y. Okay, so moving on. Now let's actually get an explicit formula for n choose k, because it's not very useful to compute, say, 100 choose 57 or something. It's going to be very hard to compute just by using Pascal's triangle, or even by using the binomial theorem. I guess you could FOIL out 100 power binomial, but that's not really helpful. It's usually you use the binomial coefficient to expand binomials instead of the other way around. So to motivate an explicit formula, which we're going to prove by induction, let's first switch back to lists. And so the only thing different between a distinct element list and subsets is that, order doesn't matter for subsets. And I don't have to talk about repetition here because I'm talking about distinct element lists anyways. I don't have repetition. So it's only order that's different between distinct element lists and subsets. So if order did matter for a subset, right, then speaking of subsets would reduce to speaking of lists. And so we just have that n choose k equals n factorial over n minus k factorial. That's the formula we saw at the beginning. That's the formula of k-size lists. Well, k-size, sublists of an n-size list. And this would be if order did matter for a subset. And so, if order matters, I guess in some sense, you have more combinations. So one thing you can tell yourself is that n choose k is going to be smaller than this in the real case. But how exactly, what do we need to remove from this n factorial over n minus k factorial? Well, because order doesn't matter, all we want to get rid of is the reordering uniqueness of those lists, For every reordering of a certain list, we just want to, collapse those into just one element in this P and K set that we are considering when we're considering the size of n choose k. And so, each list has size k, and so there are k factorial ways to rearrange them. So what we're going to want to do is divide this whole thing by k factorial, because we're removing all the rearrangements. So dividing by k factorial gets rid of reordering, so it gives us n choose k equals n factorial k factorial times n minus k factorial. So maybe you're convinced. If you're not convinced, well, the proof is going to convince you that this is true, because it's a proof. And I guess in some sense you could consider this a proof, but maybe it's a little too vague to really consider it as a proof. So let's go into the next slide. So we're going to prove this by induction. We'll start from explicit formula and just show that it's true. So it's not really a derivation as much as a proof. So from a base case, clearly 0 choose 0 is equal to 1, because that's 0 factorial over 0 factorial times 0 factorial. If we take by convention that 0 factorial equals 1, then this is going to be equal to 1. And, that's just how it is with factorial. 0 factorial is equal to 1. And I guess in some sense, you could consider the empty list as being a proper rearrangement of a zero element list. Like doing nothing counts as a part of it. So now let's assume that I choose j equals I factorial over j factorial times I minus j factorial for j smaller than I. And so, that's our inductive hypothesis. And this is for all the I smaller than n, if n is bigger than 1, or some n, right? So I take some integer, some big integer n, maybe, big or small, and I say that for all the I that are smaller than n, then this is true. And I say for j smaller than I, because, when j is bigger than I, we're just going to have this being equal to 0 anyways, so we don't really care. So for k equals 0, or k equal n, clearly n choose k equals n factorial over k factorial times n minus k factorial. And, I'm just checking for this because I wrote j is smaller than I, but in fact, I'd have to say j is smaller than I and bigger than 0 if I don't consider that a negative thing inside this would give us a 0. It's kind of like when we did with our recurrence formula earlier. But in this case, we can explicitly state that for k equals 0 and k equals n, then this is true. And you can check it yourself, k equals 0, k equals n, you need this here to be equal to 1. So if you just plug it in, you'll see that this fraction ends up being 1. So for k is smaller or equal to n minus 1, or just smaller than n, and bigger than 0, we're going to have n choose k equals n minus 1 over k minus 1, well, n minus 1 choose k minus 1, plus n minus 1 choose k by the recurrence formula. And so, expanding that, we've got n choose k equals n minus 1 choose k minus 1, plus n minus 1 choose k. And so each of those I can apply the explicit formula to, because we're assuming that it's true for those guys smaller than n choose k. So we've got n minus 1 factorial over k minus 1 factorial times n minus k factorial, right? So why do I have n minus k factorial here? Because I've got n minus 1 minus k minus 1, so that's n minus 1 minus k plus 1, and so the 1's cancel, so I've only got n minus k. And then for this one, I've got n minus 1 factorial over k factorial times n minus 1 minus k factorial. So that's just, applying the inductive hypothesis. And now we can manipulate things a little. So let's note that if I multiply this guy top and bottom by k, and remember multiplying a fraction top and bottom is like multiplying by 1, so it's just going to be the same thing. So if I multiply top and bottom by k, then at the bottom I'm going to have k times k minus 1 factorial, that's just k factorial, times n minus k factorial. And at the top I'm going to have k times n minus 1 factorial. And then, this is just to get the denominators the same. Here I can multiply by n minus k to get n minus k minus 1 factorial times n minus k is just going to be n minus k factorial. So that I've got n minus k at the top times n minus 1 factorial all over k factorial times n minus k factorial. And so now I can combine the numerators to get k times n minus 1 factorial plus n minus k times n minus 1 factorial. I can factor those to get k plus n minus k, all times n minus 1 factorial. And k minus k is 0, so you've got n times n minus 1 factorial, which is just n factorial itself. So you've got n factorial over k factorial times n minus k factorial, which is exactly what we're looking for. And so that by induction, that's going to complete the proof. And so in the next video, we'll be looking at some more properties of Pascal's triangle using, first of all, using the explicit formula for the binomial coefficient, because the binomial coefficient is the generator for Pascal's triangle, and using representations of naturals in different bases, which is a nice tool to have for numbers in general. And then once we're done with that, we'll finally move on to congruence arithmetic, and that will be in 2 videos. So that's going to be fun.